Okay, welcome back everyone. Let's now continue our discussion on the second law of thermodynamics. In particular for this lecture, or this part of the lecture, we will be discussing more problem solving, in particular steam problems for energy balance of closed systems. And for a brief recap of our last lecture, and we have derived last lecture that for a closed system, delta U is equal to Q plus W. And W is equal to negative integral of PdV. So some notes on this, negative W is equal to negative integral of PdV. If V ang gamit natin, W is in terms of energy per mole. Pero if negative integral of P dVt, as in our previous example, W will be in energy units. Okay? So if you want to get a total energy from this, gawin mo lang multiply by the number of moles to get the total energy. Okay, so let us now consider the first example. So we have a frictionless piston cylinder device which contains 10 pounds of steam at 60 psia and 320 degrees Fahrenheit. Heat is now transferred to the steam until the temperature reaches 400 degrees Fahrenheit. Determine the work done by the steam during this process and the total heat added if the piston is free to move up and down to maintain a constant pressure inside the piston cylinder device. Okay. So based on this piston is floating. So heat flows inside the system, but the piston itself adjusts whether up or down in order to maintain a constant pressure. So this now determines the total work done by the steam during this process. So first, let us quantify the initial state. So energy balance natin, delta U is equal to Q plus W, and delta U is equal to U2 minus U1. Now, in this energy balance, wala tayong maka-cancel. Okay? Di siya adiabatic. There's heat transfer. Okay? Tapos, there's a change in state from 320 to 400 degrees Fahrenheit. So, delta U cannot be cancelled out. And work, syempre meron yan. So, delta U is equal to U2 minus U1. Let us now quantify first kung ano yung values ng U2 and U1. So, state 1 is steam at 60 psia and 320 degrees Fahrenheit. And from a steam table, we can read the following values. So U1 is equal to 1109.6. Ito. And U2 is 1140.9. So delta U is equal to 31.3 BTU per pound. Next, how do we calculate the work? Okay, so we know that work is equal to negative integral of PdV. So we need to quantify the change in volume. So work, negative integral of PdV from V1 to V2. But for this entire process, the pressure remains constant. P is constant at 60 psi. So we can take it out of the integral and evaluate dV from V1 to V2. Now, on evaluates the V1 and V2, we could take a look at the specific volume of state 1 and state 2. Specific volume of state 1, 320 degrees Fahrenheit, 60 psia, which is 7.4863, and CV1, and V2 is 8.3548 cubic feet per pound. So this is V2. And as you can see, we have an expansion process. Okay. W is now negative P delta V, since integral of dV is just delta V. And calculating W, negative 60 pound-force per inches squared, convert this now into pound-force per feet squared, multiplied by delta V, which now gives us W is negative 7423.40 foot-pound-force per pound mass. So this is now the total work done, or not actually, the specific work done by our system. So negative expansion nga siya. Okay. But then, we now need to quantify the amount of energy transferred, how much heat was transferred to the piston. So by energy balance, we have to calculate for Q. But the units don't match. 31.3 BTU per pound mass. Ang work natin ay negative 7423.40 foot-pound force per pound mass. So we have to convert work into BTU. So just use the conversion factor, and from energy balance, you can get the Q, which is 40.84 BTU per pound mass. So from the sign convention, Q is positive, therefore tama nga na heat was added to our system. Okay. Let us now consider this second example. We have a rigid tank divided into two equal parts by a partition. Okay. One side of the tank contains 5 kilograms of water at 200 kBa and 25 degrees Celsius, while the other side is evacuated. The partition is then removed, and water expands into the entire tank. The water is allowed to exchange heat with its surroundings until the temperature in the tank returns to its initial value of 25 degrees Celsius. With this, determine the final pressure and state of the system, and the fraction of water that vaporized, if any, and B, the heat transfer for this process. So first, we have drawn our system boundary to be the whole tank. Kahit na merong evacuated space, the water will eventually go into the evacuated space. Okay? So we consider this whole tank as our system boundary. But the system boundary, take note, did not move. Okay. So now, to start with problem solving, let's quantify first the initial conditions in the process. So for the initial conditions, ano muna yung initial specific internal energy and the initial specific volume. Okay. So now we have a liquid, P1 200 kPa and T1 25 degrees Celsius. So we know from experience na if the pressure is 200 kPa, most likely the boiling point is above 100 degrees Celsius. So we have a subcooled liquid, but we know that the internal energy is approximately just a function of temperature. So we can approximate the internal energy or even the properties of water for at 25 degrees Celsius only. Okay. So initial conditions, U1 is 104.83 kilojoules per kilogram. Okay. So we approximate the saturated liquid internal energy at 25 degrees Celsius to be the temperature of any liquid at 25 degrees Celsius. There's some actual changes, but for reasonable approximation naman siya. And we will do the same for the specific volume. Okay? For the specific volume, may konting change, pero pwede, enough approximation na yan. Tignan nyo, 0.001 and then 0.00103. Okay? Next, let's now calculate the total initial volume. So the total initial volume, we have 5 kilograms of water times the specific volume, which would gives us 0.005 cubic meters. Let us now calculate the total final volume. Since this space, okay, the initial total volume, this is half of the initial, this is half of the tank volume. We can now obtain the final volume, which is 0.01 cubic meters. So, yun. Meron na tayong total volume of the final state, 0.01 cubic meters, and we know that the mass of water inside the system is constant at 5 kilograms. So merong konting water na nag-vaporize dito. But the mass is still constant at 5 kilograms. We can now calculate the final specific volume of water. So final specific volume of water is given by the final total volume, 0.1 cubic meters, divided by 5 kilograms. So V2 is 0.01 cubic meters divided by 5 kilograms, which gives us 0.002 cubic meters per kilogram. Now, we know that this is at 25 degrees Celsius, and if you take a look at the specific volume of saturated liquid water and saturated vapor at 25 degrees Celsius, 0.002 is in between these two specific volumes, meaning we have a mixture of saturated water and saturated vapor in this final state. Since meron na tayong mixture, let's now calculate kung ano yung actual quality ng system natin. So recall, V2 is equal to 1 minus X, the quality, times the saturated liquid property, plus X times the saturated vapor property. And calculating, you can get the actual quality of the system, which is 0.00023. Okay, so very minimal yung nag-vaporize, pero meron pa rin. Okay. Now, let us calculate the internal energy. So to calculate delta U, we need U2. So to get U2, since this is a mixture of liquid and vapor at saturation, again, use the mixing formula for saturated liquid and vapor, and you can get U2 to be 104.98 kilojoules per kilogram. So now that we have quantified the initial and final states, the initial specific volume, final specific volume, and initial internal and final energies, let us now proceed to the energy balance calculation. Now for energy balance, we know that delta U is equal to Q plus W. But the system boundary does not change, meaning W is equal to 0. Wala tayong system movement, system boundary movement. So meaning delta U is now equal to U2 minus U1, which is equal to Q. And we've already previously calculated U2 and U1. So delta U is 104.98 minus 104.83, which will give us 0.15 kilojoules per kilogram. And delta U is equal to Q, meaning Q is also 0.15 kilojoules per kilogram. And to calculate the total heat transfer for this process, we just simply need to multiply this delta U per unit mass by the total mass of the system, which is 5 kilograms, giving us the total heat transfer to be 0.75 kilojoules. Okay, let's now proceed to the last problem. You have two rigid tanks connected by a valve. Tank A contains zero point 0.2 cubic meters of water at 400 kPa with 80% quality. Tank B contains zero point 0.5 cubic meters of water at 200 kPa and 250 degrees Celsius. Now, when the valve is opened, the two tanks eventually come to the same state since they will mix. The contents will mix. Now determine the pressure and the amount of heat transferred when the system reaches thermal equilibrium with the surroundings at 25 degrees Celsius. So from the problem statement, we have two tanks which has an initial temperature of probably over 25 degrees Celsius, but they will eventually come to thermal equilibrium upon mixing, okay, and the thermal equilibrium with the surroundings at 25 degrees Celsius, meaning most likely heat is transferred out as indicated by this arrow. Okay. So to start this problem, the steam table details have been provided, okay, but in usual problems, you should be able to find the necessary steam table details. Okay. First, let's determine the specific volume and internal energy for both tanks' initial conditions. So for tank A, you have zero point 0.2 cubic meters of water at 400 kPa with 80% quality, meaning to get U1 and V1, you will read it from the saturated steam table. Tapos, 80% quality pa, so you'll make use of the linear mixing formula. So at 400 kPa, okay, the actual V1 is somewhere between these two values, and actual U1 is actual between these two values. Sorry, VA1 and UA1, since we have two initial conditions for the two separate tanks. Now, tank B contains zero point 0.5 cubic meters of water at 200 kPa and 250 degrees Celsius. So this is a superheated steam table. So this is already VB1 and UB1. So calculating the saturated mixture properties, you should get VA1 to be 0.37015 meter cube per kilogram and UA1 2163.324 kilojoules per kilogram. And obviously for VB1 and UB1, read them as is from the superheated steam table. Ayan. So na-determine na natin ngayon kung ano yung initial conditions for both sides of the tank. Okay. So let's proceed to some calculations from this. Let's now try to calculate kung ano yung initial mass of both tanks. So calculate for initial mass of tank A and tank B. So tank A contains 0.2 cubic meters of water with a specific volume of 0.37015 meter cube per kilogram, while tank B contains zero point 0.5 cubic meters of water with a specific volume of 1.1989 meter cube per kilogram. And calculating, you can get the mass of tank A, initial mass of tank A, and the initial mass of tank B. Now, at the end of the process, when the two contents of the two tanks finally mix, water does not escape the tank. Wala namang way para rin mag-escape. Therefore, the total mass of water inside the two tanks should be constant at any period in time. Therefore, the final mass of the combined tanks A and B at the end of the process is simply equal to the sum of the initial masses of the two tanks. So M2 is equal to MA1 plus MB1, which is 0.95737 kilograms. Now, the tank itself is rigid, so the total volume of the two tanks did not change. Thus, if this tank A is 0.2 meter cube and tank B is 0.5 meter cube, therefore the final volume of the two tanks, assuming the volume of this valve, the pipe maybe, kasama na yan, at least itong volume na yan, is negligible. Therefore, the final total volume should be equal to the sum of the two initial volumes, which is zero point 0.2 plus zero point 0.5, giving us 0.7 meter cube per kilogram. So now, alam na natin yung final and initial mass and final and initial volumes, total volumes. Using these two, you can now calculate the final specific volume of our system. So V2 is equal to the total final volume V2T over M2, the total final mass, which gives us the total final specific volume of 0.73117 meter cube per kilogram. So now, how did that help us? Calculate natin the final specific volume when the two tank contents are combined is 0.73117 meter cube per kilogram. And we have also determined from the problem statement that the system reached thermal equilibrium with the surroundings at 25 degrees Celsius. Given this, we now have 2 degrees of freedom in order for us to fully define all intensive variables of our system. So let us now look at the steam table. So ito, given na sa inyo. And if you take a look at 25 degrees Celsius in the saturated steam table, the final specific volume is 0.73117 meter cube per kilogram. And this final specific volume is between the specific volume of a saturated liquid, water, and saturated vapor at 25 degrees Celsius. So alam na natin na meron tayong mixture of liquid and vapor. We can now calculate the quality of our system. So using the linear mixing formula, we can now get the quality of our system to be 0.01685 or approximately 1.69% vapor. And calculating, you can also get the final internal energy, which is between these two. So U2 is 143.65695 kilojoules per kilogram. So ngayon, na-quantify na natin lahat ng initial and final states. Let us now proceed to the energy balance. So since the tanks are rigid, hindi nag-move yung system boundary natin, work is zero. Thus, energy balance will result to delta U is equal to Q. And the total delta U is equal to M2U2, the total final state, total final internal energy, minus the total initial energy given by the two tanks. So M2U2 minus sum of M1, MA1, UA1 plus MB1, UB1. And substituting the values that we have calculated earlier, we can now get the total delta U, which is negative 2170.48 kilojoules, which is also equal to the heat transfer. And from this, we can see that Q is negative, meaning heat was lost in the process. Okay, so this now ends our lecture for the energy balance for closed systems And our next topic will now be still energy balance by closed systems, but now involving ideal gas process calculations. So ngayon, puro steam. Next will be puro mga ideal gas calculations. Okay, so that's it. If you have any other questions, please message me as soon as possible. Thank you.